Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
Okay, let's just jump right in. We're about to unpack a concept that is, well, it's so massive, it really does change how you see everything.
Really does.
We all look up at the night sky and we see the stars scattered, right? It looks like this beautiful, sprawling chaos.
Infinite randomness.
Exactly. But that pattern, that apparent randomness, is maybe one of the greatest illusions in the universe. Our sources this week show that everything, every single galaxy, every cluster, isn't random at all.
No, it's meticulously organized. It's all part of this immense, mostly invisible structure.
The grand architecture of everything.
It forces a complete rethinking of, cosmic perspective. So if you're prepping for a meeting or just trying to get up to speed on this is your shortcut. This is the structure that holds the universe together.
Absolutely. So our mission today is pretty straightforward. We've gone through the material and we're going to pull out the critical insights on this thing. The largest known structure in existence, which scientists call the cosmic web. We want to map this vast, intricate, three-dimensional tapestry and understand what it looks like, what it's made of, how it formed, and maybe most importantly, where it's all going.
You have to start with the scale. The initial shock factor is always the scale.
It's mind-boggling.
It is. We are talking about a framework that spans billions of light years. It organizes trillions of galaxies. To even begin to grasp it, you have to mentally step back. So far, an impossible distance.
Right.
So far, that entire galaxy clusters, each with thousands of galaxies, just shrink down to look like little glowing dust motes. And only then, only from that perspective, does the pattern emerge.
And the analogy in the source is just stunning. It looks like a neural network.
Or the inside of a biological cell. It has this organic feel to it, which is so strange when you're talking about, dark matter and galaxies.
It's the skeleton that reality hangs on.
It is. And that skeleton, that architecture, it basically has three main parts. First, you've got the filaments.
For spreads.
Exactly. Luminous, elongated, string-like structures stretching across space. You can think of them as cosmic highways.
The arteries of the universe.
Perfect analogy. Then you have these slightly denser regions, which are often called walls or sheets. They're flatter, sort of like the walls of a sponge.
Okay.
And third, and this is maybe the hardest part to wrap your head around, you have the voids.
The nothingness.
The enormous, almost completely empty bubbles of space that are surrounded by all those glowing filaments.
So it's this giant cosmic sponge, dense knots, and these huge empty holes. I think we have to start with the holes because that level of emptiness it's genuinely unsettling.
It really is.
When we talk about empty space, we're usually just talking about the vacuum between planets or stars. This is something else entirely. We're talking hundreds of millions of light years across.
These are regions that defy our whole concept of cosmic density. They're defined by what gravity lost.
What it couldn't hold on to.
Exactly. The voids contain maybe 1/10 of the average density of galaxies you'd find elsewhere. There aren't perfect vacuums. There's still some stray dark matter and gas in there, but galaxies are just incredibly rare. Gravity has spent billions of years draining all the matter out of them and into the filaments.
Which brings us to this one specific and frankly kind of terrifying example from the sources.
Yep.
The Bouvet's void.
Yes. The Great Nothing.
What a nickname.
It earned it. This one void is about 330 million light years across.
So, just to put that in perspective, if you were traveling at the speed of light, it would take you 330 million years to cross it.
Just to get from one side to the other.
That's just an insane scale, and the punchline is what's inside it. Rather, what isn't.
Right. Within that gigantic volume, a space where you'd statistically expect to find, thousands of galaxies, astronomers have only found about 60.
60. In a space that big.
They're just these tiny, lonely pinpricks of light separated by unimaginable distances. It is the most isolated place we know of.
So imagine, just for a second, imagine you're part of some advanced civilization and you evolved in one of those 60 galaxies deep inside the great nothing.
Your entire view of the cosmos would be completely different.
You'd look out into the night sky and see nothing. Almost literally nothing. The next galaxy would be hundreds of millions of light years away. You wouldn't even know it was there.
Your entire cosmology would be built on this profound, crushing sense of isolation.
Yeah.
You might never even realize that a larger structure existed.
It just underscores how connected we are by comparison, which I guess brings us to the places where all that missing matter ended up.
The filaments and the nodes. This is where the vast majority of all the normal matter in the universe is concentrated. It's why they glow in our surveys.
And the sources are clear that these aren't just static strings of galaxies. They're described as active channels, like cosmic rivers.
That dynamic part is crucial. Gas is constantly flowing along these filaments, pulled by the gravity of the dark matter that forms them. It's this flow that channels matter and energy toward the center.
It's like a cosmic irrigation system.
That's a great way to put it. It's constantly refueling the most active regions of the universe. Without it, star formation would have just fizzled out billions of years ago.
And all of these cosmic rivers, these flows, they eventually converge.
They do. They converge at the densest points, the nodes. These are the gravitational sinks of the universe.
The cosmic cities.
The cosmic megacities, really. This is where galaxy clusters form, the most massive gravitationally bound things we know of. We're talking thousands of galaxies with masses of a quadrillion suns.
And they only form at these intersections.
Exclusively. At the nexus points where multiple filaments cross and matter just piles up, the density there is, well, it's astronomical.
So the voids are the empty suburbs, and the nodes are the dense downtown cores. But why do we even care about studying the voids? What do they tell us, beyond just being empty?
They're actually fundamental to understanding the whole process. They're the flip side of structure formation. As gravity pulled matter in, the voids got bigger and emptier.
So they show us gravity's effect in reverse, almost.
And because there's so little matter, so little gravity, they're the most pristine laboratories for studying dark energy.
Ah, because dark energy is the force pushing everything apart.
And its push is most obvious where gravity is weakest. So if you measure how fast the walls of a void are moving away from each other, you get a direct measurement of dark energy's power, without all the messy interference from massive clumps of matter.
So you studied the negative space to understand the dominant positive force.
Precisely. But, this whole discussion of galaxies and gas is just the visible stuff. To really get the architecture, you have to look at the ingredients list. And it's wild.
This is the part that just bends my brain every time. We've just described this immense, beautiful structure and all of it, all the visible stuff. The stars, the gas, us. That's only about 5% of what's actually there.
5%. It's staggering. You can look at the biggest, brightest thing in the sky, and you are only seeing a tiny fraction of what's really running the show. The web is built by the invisible majority.
So let's start with the big one, the scaffolding itself.
Dark matter. That makes up about 27% of the universe.
The invisible skeleton. That's the best analogy.
It is the scaffolding. It's called dark because it doesn't interact with light in any way we can detect. It doesn't emit it, absorb it, or reflect it.
So, the obvious question. If we can't see it, how in the world do we know it's there? And not just there, but that it's building this massive structure.
The first big clue came from just watching how galaxies spin.
Okay.
If you look at a spiral galaxy, like our own, you can measure how fast the stars are orbiting the center. And based on the matter, you can see the stars on the outer edges should be moving much, much slower, just like Pluto moves slower than Earth.
Standard gravitational physics.
Right. But that's not what we see. When astronomers measured it, the stars way out on the edge were moving almost as fast as the stars near the core.
Which shouldn't be possible. They should fly off into space.
They should. The only way to explain it is if there's a huge amount of unseen mass, a massive halo of it, surrounding the entire galaxy, providing the extra gravitational glue to hold it all together.
And that unseen mass is dark matter.
That's the 27%.
Okay.
And it plays a critical role in the formation story because it had a head start.
What do you mean a head start?
Because it only interacts with gravity, it was free to start clumping together really early in the universe's history. Normal matter was getting pushed around by radiation pressure, but dark matter just collapsed.
So it built the framework first?
It laid down the tracks, it formed the invisible filaments and nodes, these deep gravitational wells, and then the normal matter, the stuff we're made of, just flowed in and settled into the structures that the dark matter had already built.
Which brings us to that normal matter, the 5% we can actually see. Mostly hydrogen and helium gas.
Right, the tracer gas. And it's not just sitting there calmly. As it falls into these dark matter wells, it gets incredibly hot, millions of degrees.
So it slams into these filaments and nodes and gets superheated.
Exactly. It gets compressed and shocked. But for stars to form, That gas has to eventually cool down and condense. That cooling process is what allows it to fall deeper into the gravitational well, get dense enough, and finally ignite into stars.
So dark matter builds the riverbeds, and normal matter is the water that flows in, cools down, and eventually lights up.
A perfect summary. But we're still missing the biggest piece of the pie.
The dominant component, dark energy.
The remaining overwhelming 68% of the universe. And its job is the complete opposite of dark matter. Dark matter clumps things together with gravity. Dark energy is this mysterious anti-gravitational force that pushes everything apart.
It's the force that's trying to tear the whole web apart.
It is. It's what's causing the expansion of the universe to accelerate. And unlike dark matter, it doesn't clump. It's everywhere, uniformly distributed through space itself.
So as space gets bigger, there's just more of it.
Exactly. More space means more dark energy, which means a stronger push, which means faster expansion. It's a feedback loop. And that's what will ultimately determine the fate of the cosmic web. It's a constant battle between gravity building it up and dark energy tearing it down.
Okay, so we have the ingredients. Let's talk about the recipe. Let's go back 13.8 billion years. This story is really about the universe going from almost perfectly smooth to this.
We start right after the Big Bang. The universe is this incredibly hot, dense plasma. And the key thing is it was almost perfectly uniform. The fact that we have any structure at all is the real miracle.
So something had to break that uniformity, and the sources say it came down to these tiny, tiny seed fluctuations.
We're talking about quantum fluctuations, variations in density that were smaller than an atom.
Wow.
This is where quantum mechanics and cosmology just collide. These microscopic spots were just ever so slightly denser, which meant they had ever so slightly more gravity. At the time, they were insignificant, but they were the blueprint for everything to come.
And then the universe expanded, and it stretched those tiny seeds with it.
Right. The rapid inflation in the first moments of the universe stretched those quantum fluctuations to astronomical scales.
Yeah.
If you look at the map of the cosmic microwave background, the oldest light in the universe, you see these tiny temperature spots.
The hot and cold spots.
Those are the seeds. Those are the places that would one day grow into the giant superclusters and the vast empty voids.
And that kicked off this runaway process, what the sources call gravitational instability.
Which sounds complicated, but it's actually the simplest idea. It's just gravity doing what gravity does. The regions that were a little bit denser had a little bit more gravity.
So they pulled in more stuff.
Which made them denser, which gave them more gravity, which pulled in even more stuff. It's a positive feedback loop that took hundreds of millions of years to play out.
Like water flowing downhill. The initial fluctuations were just tiny dips, but gravity makes sure all the water flowed into them, which carved the dips into deep valleys.
That's a fantastic analogy. Matter literally flowed from the less dense regions to the more dense regions. The empty places got emptier, and the dense places became the filaments and nodes.
And dark matter was leading the charge the whole time.
It had to. Normal matter was still tied up with radiation being pushed around. Dark matter wasn't. It just felt gravity. So it was free to collapse first and create that initial framework.
It dug the riverbeds.
It dug the deep gravitational channels, and then the normal matter just followed those paths. It streamed in, cooled down, and lit up the first stars and galaxies.
And we actually have a timeline for this. When was the structure, visibly in place?
It's surprisingly early. By about 400 million years after the Big Bang, the basic architecture was already there. The universe was no longer smooth. The pattern of filaments and voids was locked in.
And from there, it just grew.
It grew hierarchically. Small things merged to make bigger things. Galaxies merged into groups. Groups merged into clusters. The filaments got thicker and hotter. The voids got bigger and emptier. It's a process that's still happening right now. The universe is still being built.
So we have this vast, ancient structure, mostly made of invisible stuff. The practical question then is, how do we map it? How do you see the unseeable from one tiny planet? For a long time, this was all just theory, wasn't it?
Oh, absolutely. It was beautiful theory, and it came out of simulations, but getting observational proof was one of the great challenges of modern astronomy.
Because you can't see the dark matter, and the gas in between the galaxies is just too faint and spread out.
Exactly. So for decades, we could only infer it by looking at how galaxies were clumped together statistically. The first huge leap forward was when we just got much, much better at mapping the things we could see.
Breakthrough number one, the massive galaxy surveys.
Right. Projects like the Sloan Digital Sky Survey. They didn't just take pictures. They systematically map the three-dimensional positions of millions of galaxies.
So not just where they are in the sky, but how far away they are.
That's the crucial part. You measure the redshift of the light, which tells you the distance. And when you plot millions of those dots, location plus distance, in a 3D map,
the web just appears.
It just pops into view. Suddenly, the simulations were real. You could see the filaments, you could see the walls, you could see these enormous voids. It was the first powerful visual proof.
But that's still just mapping the 5%, the bright lights. How did we prove that the space between the lights, the filaments themselves, were actually full of gas?
For that, you need a clever, indirect trick. It's called quasar absorption.
So you use quasars as flashlights?
The brightest flashlights in the universe. A quasar is a supermassive black hole at the center of a distant galaxy, and it's shining brighter than 1 trillion suns. We use that incredibly bright light as a backlight.
And as that light travels across billions of light years to get to us, it has to pass through the cosmic web.
It passes right through the gas in the filaments. And as it does, that gas hydrogen, helium, absorbs very specific wavelengths of the light. It leaves a sort of barcode, a set of absorption lines, imprinted on the quasar spectrum.
It's like seeing a spider web because of the dewdrops on it. You don't see the web itself, you see the effect it has on the light passing through.
That is the perfect analogy. And by reading that barcode, we can tell exactly what kind of gas is out there, how hot it is, how dense it is, all along that line of sight. It proved the space between galaxies wasn't empty. It was full of this hot, diffuse gas flowing exactly where the models said it should be.
Incredible. Okay, so that's the gas. But the biggest piece is still the dark matter skeleton. How do you map the 27%?
For that, you have to use Einstein. You use general relativity. The technique is called gravitational lensing.
This is where mass literally bends the fabric of space-time.
Right. So a massive structure, like a filament of dark matter, will warp the space around it. Any light from a much more distant galaxy passing by that filament on its way to us will have its path bent.
So the image of that background galaxy gets distorted.
It gets subtly stretched or magnified or warped. By measuring those tiny, tiny distortions in the shapes of thousands of background galaxies all across the sky, you can work backwards. You can create a map of where the unseen mass must be to cause those distortions.
You're literally mapping the invisible by seeing how it bends space.
It's the most direct evidence we have for the dark matter scaffolding. It shows us unequivocally that the visible galaxies are just tracing this much larger, much more massive invisible structure.
And it's not stopping there. The sources mention new techniques are coming online.
The holy grail now is to move from indirect detection to directly imaging the faint glow from the filament gas itself. Radio telescopes are trying to detect the specific signal from neutral hydrogen atoms.
And X-ray telescopes for the hot gas.
Yes. X-ray telescopes are looking for that superheated plasma where the filaments meet and slam into each other. There have even been some recent tentative claims of directly detecting the faint X-ray glow from the filaments themselves. If that's confirmed, I mean, that would be like turning on the lights for the entire structure.
So this whole mapping project, it's not just an abstract exercise. This web actually controls the fate of every galaxy inside it, including ours.
Absolutely. It's a massive environmental regulator. Where a galaxy lives in the web determines its entire life cycle.
It's all about location, location, location.
It really is. Let's take the two extremes. You've got the galaxies in the dense clusters at the nodes, the cosmic cities.
The busy downtown core.
Right. And it's a rough neighborhood. Galaxies there tend to stop forming new stars. They get quenched.
Well, they're surrounded by stuff.
They're surrounded by hot stuff. The gas in those clusters is so hot and dense that it actively strips the cool star-forming gas right out of any new galaxy that falls in.
Really?
And the heat prevents any fresh, cool gas from flowing in to replace it.
So they're starving in a land of plenty.
Precisely. They run out of fuel.
Yeah.
Now, compare that to galaxies living out on the filaments, the cosmic highways.
They're in the sweet spot.
They are, because the filaments are constantly channeling fresh, cool gas in from the voids. So those galaxies get a steady supply of fuel and can keep forming stars for billions of years. And then, of course, you have the poor galaxies in the voids.
If you can even find them.
They're rare, they're small, and they are completely starved of new material. They really struggle to form stars at all.
So the web is like this giant cosmic circulatory system feeding some parts of the universe and starving others. And now we can actually see it happening.
We can. Astronomers have started finding what they call filament galaxies. galaxies that look like they're forming right inside the gas streams of the filaments themselves.
So we're catching them in the act.
It's like a real-time view of galaxy assembly. It's incredible.
Which, of course, brings it all back home to us, to our cosmic address. We used to think we were in a pretty unremarkable spot, but this changes that, doesn't it?
It completely changes it. We now know we don't live in some random patch of space. We live on a filament.
Okay.
Our local group, so that's the Milky Way, Andromeda, and a few dozen smaller galaxies, is on the outskirts of a larger structure called the Virgo supercluster. But even that wasn't the full picture.
This is the Laniakea revelation.
Laniakea, it means immeasurable heaven in Hawaiian. And it's our true, enormous cosmic home. It's a structure that spans over 500 million light years and contains the mass of 100 quadrillion suns.
And the way they defined it is what's so cool. It's not just about what's close to us.
No, it's defined by motion, by kinematics. Astronomers mapped the velocities of thousands of galaxies, and they found that every galaxy within this huge region is flowing inward toward a common center of gravity, a place called the Great Attractor.
So we're all part of one giant cosmic river basin.
We are. We are part of one single, cohesive, flowing superstructure. We live in one of the major gravitational basins of the known universe.
There's such a profound sense of connection in that. You know, it's easy to feel small and isolated, but this shows that we're not.
Not at all. We are physically connected through this network to every other galaxy we can see. The very atoms in your body were forged in stars, which formed from gas that flowed along these filaments to get here. Our existence is a direct consequence of this structure.
So we've seen how it was born, how it grew, and where we live inside it. But the web isn't forever. It has a future. And that future is dictated by that 68%, by dark energy.
Right. The story of the web is this cosmic battle between gravity, which built it, and dark energy, which is trying to tear it apart, and ultimately dark energy wins.
So how does it happen? How does this structure dissolve?
The accelerating expansion of space is happening between things that aren't gravitationally bound. So our galaxy cluster is bound together, but it's not bound to the next big cluster over.
And the space between us is stretching faster and faster.
So fast that trillions of years from now, the distance between clusters will be expanding faster than the speed of light.
Which means the filaments connecting them will stretch, thin out, and break.
They'll break. The connectivity will be gone. The models show each galaxy cluster will become its own isolated cosmic island.
Cut off from everyone else.
Completely cut off. So much so that any civilization living in that future island wouldn't even be able to see the other islands. The light would be stretched so much it would be undetectable. Their universe would literally shrink.
That's a lonely thought.
And inside those islands, the galaxies will all merge into one giant elliptical galaxy. And because the supply of fresh gas from the filaments is gone forever, star formation will eventually stop. The universe will become a collection of dark, silent, isolated islands.
From this vibrant, interconnected web to that, wow. But let's shift to something a little less somber. The sources point out that this structure, this pattern, isn't unique to the cosmos.
No, and this is one of the most fascinating parts. You see the same pattern everywhere. It's a mirror in nature.
Like the neural network of the brain.
Exactly. Neurons as nodes, connected by axons as filaments. It's the same topology. Or zoom way down. Inside a single biological cell, you have the cytoskeleton, this web-like structure holding everything in place. You see it in river deltas, in the way lightning forks, in the internet. Hubs and connections. Right. And the sources are clear this isn't a coincidence. It's because of the underlying mathematics. Whether you are efficiently moving matter with gravity or efficiently moving information through a computer network, the most optimal way to build a network often results in this same hub-and-spoke architecture.
So astronomers are actually using algorithms from neuroscience to study the cosmic web.
They are. They're using network theory to analyze its connectivity, which has turned cosmology into this amazing cross-disciplinary field.
And all of this makes the web itself a giant physics laboratory.
The ultimate physics lab. You have the most extreme conditions imaginable, the densest, hottest regions in the nodes, and the most pristine vacuums in the voids. The scale is perfect for testing our fundamental theories.
You can test gravity on a scale you could never, ever replicate here on Earth.
Right. And by studying the web's precise structure, how it grows, how the voids expand, we can test our ideas about dark matter and dark energy. Some people think we might even find hints of new physics, something beyond our current standard model, hidden in the fine details of the web's architecture.
And yet, after all of that, after mapping this incredible thing, The biggest mysteries are still there.
The mystery continues. That's the honest truth. We've mapped the skeleton, but we still don't know what the bones are made of.
We don't know what dark matter is.
We have no idea what particle it is. And we don't know what dark energy is, fundamentally. We've given names to our ignorance, in a way. But every new map, every new survey gets us one step closer to answering those questions.
It's just amazing that we can even ask them, that we can piece all this together from one tiny world.
So if we're going to boil this all down, to summarize the key insights from all this material, I'd say there are three huge takeaways.
First, the sheer scale. The cosmic web is the biggest thing there is, a network of filaments and voids spanning billions of light years. Second, it's made of invisible stuff. The universe is dominated by 27% dark matter building the structure and 68% dark energy tearing it apart. The visible 5% is just along for the ride.
And third,
It's this dynamic, evolving thing. It was forged by gravity out of tiny quantum seeds, but its ultimate fate is to dissolve thanks to dark energy. It's a temporary structure.
which completely changes your perspective, doesn't it? The universe isn't just random chaos, it's ordered. And we live in a very specific place in that order, on a filament, inside Laniakea, connected to everything else. For now.
And the fact that we can map it, that we can track the unseen through things like gravitational lensing, is just a triumph of human curiosity.
It really is.
Yeah.
So that leads us to our final thought for you to chew on. If this cosmic web, this largest of all structures, is temporary, if it's destined to dissolve as dark energy pushes everything apart, how does knowing that fragility, that ultimate dispersal, change your perspective on cosmic time and our own brief moment here inside the flow of Laniakea? What does this idea of a temporary universal architecture inspire for you? Something to think about the next time you look up at those stars. And remember, they are anything but random.